Well, hi. Don't blame me if your FETs burn up when you build a water heater. This is my new water heater control. I got the circuit boards in. I'm starting to build these. And I bought some FETs. I bought a variety of them. And this is an IRFP 90N20, which is supposed to be a 93 amp FET that can take 200 volts. And it has 23 milliohms of resistance, and that's pretty low, but that falls into the exotic area. You know, that's higher current than a lot of 200 volt FETs, and well, those are the things people want to fake because they're a little bit more expensive. So I have this, if you notice, I have no driver chip in there, and this is something new. I'm using screw terminals on this water heater board so people can change FETs. The ICs are socketed, so you know, if there are problems, a lot of you neophytes will be able to fix these by just replacing a FET or a chip. And you know, you just stick it in, screw it down, and you're on your way. But I'm using it for testing, and I got two 1 ohm resistors here. I got the power supply set at 10 ohms, so it should be about 5 amps maximum going through here. And so I'm going from this gate through this resistor, through another resistor, to the gate right here. This is the positive side. This is the drain of the FET, or what the center pin is. And it's important that, you know, little resistances matter a lot. So if you take your voltmeter and put it right on here and right on there, you'll have the exact resistance of the FET. And so again, this is 10 volts positive, and you notice that we got 3.94 volts. Well, that's pretty high. So this is a fake FET, not just a little fake, but really fake. Now, like I say, here's what we're doing. The drain, we're measuring the voltage from the drain to the source, and that's right off the pins. And you can take whatever voltage you see there, divide it by the current, and that'll give you the resistance of that. And you can just match that up with whatever the data sheet says. You know, with these fakes, I mean, I've gotten FETs that were like, you know, 30–40% less than what they were actually rated. And you know, if you can get them cheap and you're putting them in parallel, it doesn't matter. You know, if it looks like a duck, quacks like a duck, you know, that's good enough. These applications aren't really critical. If you get into high-speed switching and stuff, then you really need a good FET. But this is slow. It's technology that's easy to copy, and still they're pawning this crap off on us. Now this has 1 nanofarad of gate capacitance, so it does seem like it's a FET of the right size, but it's just enormous resistance. At first I thought it was an IGBT, but you know, the saturation voltage changes, so this is just some crap that came off the assembly line. So I'm going to put a good FET in here and we can see what's happening. So now we've put in an RF 250. This is a garden variety FET. You see these a lot in old MSW inverters. It's a 250 volt, I forget what it is. But it's 70 milliohms. And so we'll do the same test with it. And we got, you know, let's just say 310. As you can see, it heats up. The resistance changes. So here, plugging in the numbers, 0.310 volts divided by 4.5 amps equals 69 milliohms, and that's pretty much right on spec. So the thing you have to remember is always have your gate voltage greater than 10 volts. If you have a current limiting supply or something else that drops the voltage and you get less than 10 volts, you're not going to get an accurate figure. If you get around 5 volts, your FET's going to burn up because it's not going to turn on fully. Nice to keep about 2 to 3 amps. And only test for a short period of time. There's no heat sink on this. You know, when a FET heats up, its resistance increases. So, you know, if you can get 2 or 3 seconds and do a quick voltage check, you know, this is all it takes. And when you build your project, you'll know it actually will work. So thanks for watching, and boy, watch those cheap bargains on FETs. You don't always get what you think you bought.